So hello to all my dear friends. Once again welcome to this one shot series, and today the concerned topic is column. So after slab we have started column. So I hope the audio video is fine. Okay, yeah, I have tested it. Okay, so column, our third last topic. After this I am going to take two more topics. One would be pre-stress concrete. That would be slightly lengthier topic, and after that basics of working stress method. Okay, so let's start. So agendas for today's class is introduction to column, what all are the various codal provisions, and design of short axially loaded column. It is important for us. IS code is also important for us. And then interaction chart, chances are less, but yes, it is still required. And one numerical I have taken on axially loaded column, short axially loaded column. Okay, then dear, generally if you look at the vertical members of the building, then they are generally known as pillar, or you can say column. Column are primarily designed for taking axial loads. So columns get loads from beam, beams get loads from slab, and slab gets load from dead load as well as live load and from its above superstructure. Okay, so the main task of column is to take axial loads. Okay, but yes, sometimes due to the excessive eccentricities and all, our column is also known as column subjected to uniaxial bending or sometimes biaxial bending. For example, if I am taking a small complex, maybe like this, let's suppose there is a 3 by 3 column, total 9 columns, and over these 9 columns, if I am going to place, let's suppose 4 slabs, let's suppose I am going to place 4 slabs, slab number 1, slab number 2, slab number 3, and slab number 4. So you can see that this is 1, this is 2, this is 3, this is 4. Okay, so you can see that the column which is the most intermediate, like this, it is going to have equal load from all the 4 slabs. So more or less the eccentricity for this column A, for the interiormost column, is very less. So column A can be designed as the axially loaded column. But when it comes to these corner columns, not corner columns but these ones, so they are going to have load apart from axial load, they are going to have load only on one side. So due to that, these columns are having tendency to move in one direction, and these are known as columns subjected to axial load as well as uniaxial bending, and these extreme corner columns, let me call it C columns, they are going to compress. Apart from that, they are going to bend in this direction as well as they are going to bend in this direction. So they are going to have the dual eccentricities, and it is known as column subjected to axial load as well as biaxial bending. So depend upon the nature of loading. So these are the 3 major classifications of column. So there is one category of column which is our mostly area of interest, A, axially loaded column, and this is uniaxial bending column, and these corner ones are biaxially loaded column. Okay, biaxially bending loaded column. Okay, and one thing is more that the column may be a long column or it may be short column. Again, from RCC point of view, for our normal structures, basically we are interested in short column only, because here the long and short are defined based on the slenderness ratio, and slenderness ratio is defined as the ratio of effective length to least lateral dimension. Unlike in steel and some, we call lambda as effective length upon least radius of gyration, but here we used to call lambda as L effective upon least lateral dimension. So least lateral dimension in case of rectangular beam is smaller dimension L or B, and in square beam, in square column, sorry, it is any side. In circular column, it is the diameter of the circular column. Okay, so that is the least lateral dimension. If this lambda is less than 12, we are going to call it short column. We are going to call it short column. And but if lambda is greater than 12, then we are going to call it long column. We are going to call it long column only. Okay. So less than 12 short column, or greater than equal to 12 is known as the long column, isn't it? So greater than 12, I am putting it here, equal to I am putting it here, because some additional moments are coming there, so they are negligible if lambda is equal to 12. Okay. So our case is going to be the of short column. Okay, and lambda is defined as the effective length upon least lateral dimension. Dear, effective length over least lateral dimension. So what is the effective length? Effective length is defined as the distance between two consecutive contra flexor. In strength of material, we have derived some effective length values, like in fixed beam it is 0.5 L, in fixed free beam it is 2 L, it is in pin beam it is L by root 2, or one more case is left, I think, hinge case it is L only. Okay, but all these are the theoretical values which you have obtained by Euler's buckling load and all. Okay, and there are in annexure E you can find the value of effective length of column based on some more end conditions, partially restrained conditions. So it's my advice that go for all those effective length formulas, IS code recommended value from annexure E, from annexure E. Okay, from annexure E, I think page number 94 or 95, you can look at the effective length of the column, isn't it? Okay, so all because in exams like ESC prelims and SSC JEE, these effective length values may come directly. Okay, so for calculating the lambda, you need to calculate the L effective. Okay, dear. And yes, as I told you, if lambda value is less than 12, it is short column. But yes, if lambda value is less than equal to 3, then it is known as again short column, but the name of that special short column is known as pedestal. So pedestal are the small structures, which generally we use for footing, and they are these column only, and here the lambda value is going to be less than equal to 3. So the prime mode of failure of pedestal is only crushing only, so no chances of buckling. In fact, in short column as well, the chances of buckling are very less. But yes, when the lambda value is close to 11, 12 or 10, then there may be sometimes a combined mode of failure. Okay, okay, dear. Next, now as per the codal provisions, there are some you can say minimum and maximum percentage of steel. Okay, so code says that we do have some minimum percentage of steel, some maximum percentage of steel, some recommendations for the diameter, some spacing criterias. Okay, and some different recommendations for transverse reinforcement. Okay, and some slenderness limit criteria. So all such criterias we must know, like you all knowing what is the minimum number of bars required in rectangular column, what all are the minimum number of bars required in circular column, what should be the minimum diameter, okay, what is the minimum percentage of steel, and what is the maximum percentage of steel. So we can find all such values here. So let me start writing one by one. So first one is minimum percentage of steel. Okay, so minimum percentage of steel is basically given by it's 0.8%. I cannot use here AS, so it's ASC, because here the steel is in compression. So minimum percentage of steel is 0.8% of the total cross section. Okay, it is 0.8% of the total cross section. When it comes to the maximum percentage of steel, so maximum percentage of steel, there are total 2 cases. Case 1 when bars are not lapped, case 2 when bars are lapped. If bars are not lapped, okay, because the net steel would be more if bars are not lapped. So in that case, we can say that if bars are not lapped, then it is 6% of total cross section, and if bars are lapped, in that case it is 4% of cross section. Normally it is 4% only, okay, sorry, it is 6% only, but if it is lapped, then we need to give 4%, isn't it? Okay, dear. After that, we have to see that what all are the minimum number of bars which are required. So the minimum number of bars which are required here before proceeding to transverse reinforcement. So if I want to write minimum number of bars, so I hope you all know this. Minimum number of longitudinal bar, minimum number of longitudinal bars are 4 in rectangular column, okay. But one thing you have to keep in mind that spacing between two bars, it cannot exceed 300 mm. For example, if I do have a column like this, then spacing cannot exceed 300 mm. Okay, it should be 4 only, but in any case this spacing should not exceed 300 mm. So suppose if I do if I have a column of cross section 500 by 300, in that case you need to provide at least 6 number of bars, because 500 by 300, okay, along smaller side spacing criteria is okay, because some cover is also there, value is less than 300, but along the longer side you can see that even if the cover is of 50 and 50, still one side the spacing is going to be 400. So in that case we need to provide at least 6 number of bars. Similarly, if we are talking about circular bar, okay, so minimum number of longitudinal bar, in circular column, it is going to be equal to 6. So it can be seen that if this is our circular cross section, okay, then how many minimum number of bars we have to provide? 1, 2, 3, 4, 5, 6. Okay, so there are at least 6 number of longitudinal reinforcement we have to provide, isn't it? Okay. Now next it comes that what should be the minimum diameter of the bar. So the minimum diameter of the longitudinal reinforcement, let me write here, minimum diameter of longitudinal reinforcement is equal to 0. It is 12 mm. It is going to be how much? It is going to be 12 mm. Okay, it is going to be 12 mm. Are you getting it or not? Okay, all these are very small points, but believe me, they are literally very important here. What is the minimum diameter? What should be the spacing? What should be the maximum percentage of steel? Okay, what is the minimum percentage of steel? Okay, when the column is said to be short and when the column is said to be long. So all these things are quite critical there. Okay dear. Okay, so now let me move on to transverse reinforcement. Okay, one point I think I have missed, that pedestal. Yes, for pedestal, what is the minimum percentage of steel? For pedestal, what is the minimum percentage of steel? So minimum percentage of steel for pedestal is 0.15%. It is 0.15%. Okay, so it was also important point, sometimes it may be asked. Okay, so now after the longitudinal reinforcement we can go to transverse reinforcement. Okay, so transverse reinforcement, the very first thing, why we need transverse reinforcement? Like we do have shear stirrups in beams, similar in the same way we are having transverse reinforcement in our column. But the prime task of shear stirrups in beam is to resist shear force, and here the prime task of lateral ties, or you can say transverse reinforcement, is to resist buckling. Make a note here. Why? What is the main intention of providing transverse reinforcement? To resist buckling. Yeah, it is also true, it is going to take the lateral load, it is going to prevent shear and all in your column, but prime reason is to resist buckling. Okay. Generally, we can provide our transverse reinforcement in two ways. One is rectangular ties and another is circular helical reinforcement. Okay. So generally in helical reinforcement, the shape of the lateral ties is like this helical spiral, and in rectangular ties the assembling is easier, you can say, in that case. Okay. So whenever we have to decide, two things we have to decide while designing transverse reinforcement. First thing, what should be the diameter of the transverse reinforcement? Second thing, what should be the spacing of transverse reinforcement? Number one is what is the diameter of the transverse reinforcement. Second is what should be the spacing of transverse reinforcement. So first thing is diameter. So when it comes to diameter, so diameter of transverse reinforcement, in any case it should be the maximum of these two. Maximum of these two what? 6 mm, and phi c main by 4. So longitudinal bar diameter by 4 or 6 mm, whichever is greater. Okay, whichever is greater. Okay, or 6 mm, whichever is greater. But yes, sometimes in question there are two primary diameter, two longitudinal diameter. In that case, I will also recommend go for higher one, because our task is to provide bigger diameter in order to maintain more safety. Are you getting it or not? Okay. Now the second thing is spacing. Spacing is minimum of how much? It is 16 times of phi c and least lateral dimension and 300 mm, whichever is minimum. Spacing is minimum of these three. It is minimum of these three, and diameter may is maximum of these two. Similarly, in case of two different diameter, we have taken the bigger diameter here in order to maximize our diameter. In the same way, if I want to increase the amount of steel, it means I have to decrease the spacing. In order to decrease the spacing, so while calculating, while putting phi c, when there are more than one diameter bars, in that case I am going to use the smaller diameter bars of main reinforcement. So don't be confused here. So while calculating spacing, calculate phi c, keep phi c smaller one, and while calculating diameter, keep phi c bigger one. Okay. And suppose if somebody asks you that the diameter of your main reinforcement is 25 mm, then what should be the diameter of the transverse reinforcement? So in that case, my dear friend, 25 by 4 is 6.25 and it is 6 mm. So diameter cannot be less than 6.25. So friends, you have to go for 8 mm. So if longitudinal reinforcement diameter is 25 mm, then transverse reinforcement diameter should be minimum of 8 mm, because it cannot be less than 6.25. Are you getting it or not? Tell me. Any doubt to anyone? Now, after the transverse reinforcement, it comes to slenderness ratio. So what is the slenderness limit? Okay, so let's see this. So maximum limit of slenderness limit is given to you in two cases. Okay, and first is saying that the maximum unsupported length between the end restraint, it should not be greater than 16 times of least lateral dimension. Okay, it is 16 times of least lateral dimension. And second thing is, if it is a case of cantilever type column, means only one end is fixed and another is free. So in that case, the unsupported length, like we studied in case of beam, unsupported length, it should not be greater than 100 b square by d. Okay, are you getting it or not? So what is the maximum limit of slenderness ratio? Let me write here. So unsupported length between end restraint, unsupported length between and restraint, okay, should not be greater than 16 times of least lateral dimension. And in cantilever case, in cantilever case, or if one end of column is restrained only, then unsupported length should not be greater than 100 b square by d, where b is the overall width of the column cross section and d is the depth. Okay, plan, you can say b and d plan. Okay, is it clear? And yes, one more thing. So these two are the important clauses, 16 times of LLD and 100 b square by d. So first statement is talking about generally such columns where top and bottom both are restrained, and this category is talking about this column when only one end is restrained and another is free. Okay, now dear, when we have to study column, then there are certain assumptions. So what all are the assumptions? Assumption says that first thing is, whatever assumptions are there for beam, all those assumptions are also valid here. That is, plane section before bending will remain plane after bending, maximum compressive strain is that much. Okay, if tensile is coming, then clauses are also same here. If tension develop, then concrete is not going to take any tension. Okay, but apart from that, two more assumptions are there which is very important here. So what are they? First is the maximum strain in concrete in axial compression is 0.0020, or you can say 0.2%. Second is the maximum compressive strain at highly compressed compression fiber in concrete subjected to axial compression and bending, and when no tension is developed in the section, it shall be 0.0035 minus 0.75 times of the strain at the least compressed fiber. So let me just tell you what it is exactly saying. This assumption is saying that suppose if you have a cross section here, it is B and it is D. Okay, and if this is strain 0.0020 in perfect compression when the load is at center, and this is the scenario in extreme bending condition. Okay, here when no tension is developed, strain here is 0 and strain here is 0.0035. Now my dear friend, any practical case is going to be between them only. So in such scenario, what to do? So let me draw that differently. It's going to be like this. This is the strain at highly compressed fiber. This is the strain of least compressed fiber. So it is said that the case is going to be between this and between this. So strain at highly compressed fiber is going to be between this and this. The strain at least compressed fiber is going to be between 0 and this. So it is assumption number 2 is saying that the strain of highly compressed fiber is equal to 0.0035 minus 75 or 3/4 of strain of least compressed fiber. Okay. So very easily with the concept of similar triangle you can get this relation. You can see this is 15, 0015, this is 0020, so it is 3/4, it is also in the ratio of 3/4, it is also in the ratio of 3/4, so it is also in the ratio of 3/4. So this increment is 3/4 of this summation of LCC, isn't it? Okay. So whenever it comes to the design of column, so we have to make sure of two things. If it is a case of axial loaded short column, first, eccentricity must not exceed the minimum one. Second, it must be a short column. So in order to ensure that the column is short, we need to say that yes, lambda is L effective upon R upon LLD. It should be less than 12. Second is the calculated eccentricity. How we are going to calculate eccentricity? The calculated eccentricity L by 500 plus B by 30 or 20 mm, whichever is more. Okay, so that should be less than 0.505 of the LLD. Okay, for short axially loaded member, if E minimum as calculated above is less than 5% of the lateral dimension, then the member may be designed. For axially loaded member. And friends, in that case the PU is given by 0.4 FCK, okay, AC plus 0.67 FY into AS. So by this you can calculate the value of short axially loaded column. But yes, if somebody is saying to you that column is at 0 eccentricity, because this is going to design for a minimum eccentricity, it can tolerate the eccentricity of bigger of these two, and that must be less than this. So at least 20 mm eccentricity it is going to incorporate. Okay, so at least 20 mm eccentricity it is taking, or sometimes it is taking even more than that. Okay. But if somebody is saying to you that there is absolute 0 eccentricity, in that case how to calculate the ultimate load carrying capacity of the column? So in that case we represent the ultimate load carrying capacity of the column is by PUZ, and it is 0.45 FCK AC plus 0.75 FY AS. Okay. But yes, we are going to use this one for our design. Because it is going to take care of short column as well as of minimum eccentricity thing. Okay. I have a numerical on that. That is going to revise you all these things. Now, what would happen if the column is subjected to axial load? Okay, along with the uniaxial bending, what would happen then? So such designs we will be performing by using interaction curves. Interaction curve will look like this. Okay, on y axis it is PU upon it. This you can get by the rigorous analysis, and this is mu upon FCK BD square. Why it is happening? Okay, so the curve will look like Okay, the curve will look like this. This is known as K line. This is known as K line. K is basically P upon FCK. P is the percentage of steel and FCK is the grade of concrete. And there are too many K lines. There are too many K lines. K 0.01, 0.02, 0.03, 0.04, 0.05 like that. Too many K lines are there. So whenever the eccentricity is going to exceed the 5% of the lateral dimension, in that case we classify our column to be uniaxial bending. If both the dimensional eccentricities are exceeding the 5% of the corresponding dimension, in that case we will be calling our column subjected to biaxial bending. Okay, biaxial bending. So in biaxial bending, what we are going to do? We are going to design it by biaxial column. So same interaction chart we need to read twice. And for uniaxial bending, what we have to do? We have to find the y-axis, because Pu is known to you. We have to find the mu upon FCK BD square, because mu is also known to us. If it is not known to us, then eccentricity we know, and mu is equal to Pu into eccentricity. So based on Pu and mu, you will get your x-axis as well as your y-axis. So suppose your x-axis and y-axis are going to meet somewhere here. This is your y and this is your x. So you have fixed this K line, and let's suppose this K is 0.03 for example. So the design is very easy here. After calculating the value of Pu upon FCK BD and mu upon FCK BD square, you will get the value of K. Not if you are not fortunate enough to get the point on this curve, then you may be getting slightly here or slightly there. If it is slightly here, then it is 0.02728 like that. If it is slightly on that side, then it is 0.032, 0.033. You can interpolate, okay, visually. So once K value is fixed, then percentage of steel is known to you. What is percentage of steel? Percentage of steel is K times into FCK, where FCK is the grade of concrete. So like this, the task or design can be done. All you need to find the area of steel, and you can get the area of steel like this. Are you getting this or not? So this is the way of designing column subjected to axial load as well as uniaxial bending. But from exam point of view, what is important? That what is the property of this interaction curve? How many zones it do have? Okay. So all such properties are important. So let me again explain you the properties of this interaction curve. So this is your x-axis, okay, your mu upon FCK BD square, okay, and this is your y-axis. This is your y-axis, Pu upon FCK BD square, Pu upon FCK BD square, and your curve will be like this, okay. And here, dear, we know this is mu upon, Pu upon FCK BD, and this is mu upon FCK BD square, okay. So there are total 3 zones. Zone number 1, zone number 2, zone number 2, okay, and this is zone number 3, okay. So there are 3 zones, and there is one more variable, eccentricity variable. Like here eccentricity is 0, here eccentricity is minimum eccentricity, and here eccentricity is equal to balance eccentricity, okay. So zone 1 is minimum eccentricity zone, minimum eccentricity zone, okay. Zone 2 is compression control zone. It is compression control zone, and zone 3 is tension control zone. It is tension control zone. Okay, so these three zones are there. So here the value of eccentricity is 0, here the value of eccentricity is E minimum, here the value of eccentricity is E balance, and you can say at this axis the eccentricity value is almost tends to infinity. Okay, so in zone number 1, dear, this is the perfect zero eccentricity case. So if somebody asks you what is this strength, this you can denote by PUZ, and it is 0.45 FCK, okay, AC plus 0.75 FY into AS, and this point corresponds to your PU, it is 0.4 FCK AC plus 0.67 FY AS, okay, and here the strain is perfectly 0.0022 and 0.002, here as well 0.0020, here as well very minor conflict. On one side it is 0.0020 and on slightly more than 0.0020, and on bottom it is slightly less than 0.0020. But here as well, my dear friend, your strain diagram, because since the zone is compression control, so tension will not be developed anywhere. So this is the highly compressed concrete fiber, this is the least compressed concrete fiber. So the strain at highly compressed concrete fiber is going to be equal to, it is going to be equal to 0.0035 minus strain of least compressed fiber into 3/4, okay. And here you can say that yes, here the strain diagram would be perfectly like this. It is 0.0035, it is 0, and beyond this point, your strain diagram will look like, this. It is 0.0035 and strain diagram will look like this. We can say that in zone number 1, neutral axis is outside of the column section. Zone number 2 as well, the neutral axis is outside of the column section. Yeah, it is first time when neutral axis is going to touch your column. And in zone number 3, the neutral axis is lying within the cross section. Or what observation else can be made? In zone 1, the load of axial loads are quite high as compared to moments due to the lesser value of eccentricity. In zone 2, the value of load as well as moment are equally comparable, and in zone number 3, the value of load is quite less but the moment is more due to the higher value of eccentricity, okay, isn't it? So zone 3 can be designed just like your beam, okay, beam by LSM. So in same fashion we can design that, isn't it? So all these are the important properties of the interaction curve. Yeah, one more important point of 3, with the reduction of load, moment carrying capacity here is also decreasing. This is also point to be noted here, okay. With the reduction of load, moment carrying capacity of the column is also decreasing, isn't it? Okay, now design steps I have told you, and after that we will be seeing one numerical on the axially loaded member, So let's see that numerical. So it's quite easy and concept building numerical. So what is given here, that a RCC column of size 460 by 600, okay, it is having an effective length of 3.6 meter and it is to be designed by using LSM, okay, to support a load of 2500 kN, use M20 concrete and Fe415 steel. So before applying short axial loaded column, we need to prove that it is short column as well as axially loaded column. So first I am going to calculate column lambda. Lambda is L effective upon least lateral dimension. So L effective is 3600 mm and least lateral dimension is 460 mm. So I think this value is coming out to be how much? This value is coming out to be 7.8, okay, 7.8, which is less than 12. So it is short column. It is short column. Next check is of eccentricity check. Eccentricity check is quite logical and conceptual as well. So we know that E minimum is maximum of 20 mm and L by 500 plus B by 30. So here B by 30 is to be calculated two times. One for this scenario, okay, and another one for this scenario. I hope you got the point. So this, okay, so this one is how much? It is if it is 600 by 460 and it is 460 by 600. So on both the side we need to calculate this. One times we have to keep here 600 and other times we are going to keep here 460. When 600 I am going to put here, so it is L by 500 means 3600 by 500 plus 600 by 30. So 600 by 30 is 20 and 3600 by 5, 36 by 5, 7.2. So it is 27.2. It is 27.2 and 27.2 is less than, I guess, 5% of the 600. 5% of the 600 is how much? It is 30 only. So it is passed. So the minimum eccentricity, which is the maximum of these two, is 27.2 and that is less than 30. So it is passed. Similarly here, what is L by 500 plus B by 30? So it is 7.2 plus B by 30 is 23. So 23. B by 30, 460 by 30. 460 by 30. So how much? 5. 5.3, 5.3 and 2.2, 22 point something, 22 point something it is coming. Let's suppose 4. What about 0.05 of B? So it is 460, so it is coming out to be 23. So here also just saved. Here also the calculated eccentricity is 22 point something and it is coming out to be less than 23. So it is also just safe. So we can say that our column is short and axially loaded. It is short and axially loaded. Okay. So in that case, what to do? We can use PU. PU is 0.4 FCK AC plus 0.67 Fy into A. One more important thing, dear, whenever there is a case of helical reinforcement or spiral reinforcement, in that case simply increase the load carrying capacity of the column by 5% or multiply this by 1.05. okay. So what load we have to resist under working condition? 2500 kilonewton. So actual load which we need to resist here is 2500 kilonewton into 1.5. okay. What about FCK? FCK is how much here? FCK is 20. okay. What is area of concrete? It is 460 into 600 minus area of steel plus 0.67. Fy is 415 and ASC again we need to calculate. So dear friends, it is ASC is equal to how much? ASC is equal to how much? This we can calculate. It is coming out to be 5710. It is coming out to be 5710 mm square. Now assume 25 mm diameter. Assume 25 mm diameter. So in that case, number of bars are 5710 upon pi by 4 into 25 per square. So this is coming out to be again 11.6, so nearly it can be kept 12. So we need 12 bars of 25 mm diameter as a main reinforcement. So after the decision of main reinforcement, now it's time to come back on transverse reinforcement. So only two things are required in the transverse reinforcement. What all are those two things? First is diameter, and second one is spacing. So if I am talking about the diameter, then diameter of the transverse reinforcement can be decided based on these two parameters. One is 6 mm and another is 5c by 4. So 5c by 4 on keeping 25, it is coming out to be 6.25 mm and it is 6 mm. So what is greater? Greater is this one. So we will be using 8 mm because in any case we cannot come below 6.25. Okay, so we cannot come under 6.25. So second thing is the spacing of the transverse reinforcement, and again we have to select among three criteria. One is 16 times of 5c, another is LLD, and third is 300 mm. So here 16 times of 5c is 25 we need to keep, it is 400, it is 460 and it is 300. So out of these three, the least value is 300 mm. Okay, the least value is 300 mm. So we will be going with that spacing, we will be going with that. So design says that here we are going to provide 25 mm diameter longitudinal reinforcement, 12 mm number along 460 cross 600 mm cross section, and for transverse reinforcement we will be providing 8 mm diameter and at a spacing of 300 mm center to center. Okay, so this is the basically crux of axially loaded member, isn't it? Okay, so this is the main features, main things about column. Okay, so next two more topics are there. One is pre-stressed concrete and another is WSM basics. Okay, so we will be meeting there. Bye bye.